Have you ever wondered if some problems deserve more attention than others? Imagine a computer program that doesn't just work harder on complex problems but actually adjusts its approach based on the difficulty of the task. This represents a new paradigm in the realm of machine learning. In today's video, we're going to delve into what makes AdaTape so extraordinary. Before we dive in, make sure to hit that subscribe button and turn on the notification bell so you won't miss any of our upcoming videos. Let's start by discussing the concept of adaptive computation and how it differs from how traditional neural networks typically function. Neural networks, those powerful tools in technology that can learn from data to perform tasks like image recognition, language understanding, and more, usually employ a fixed approach regardless of whether the task is easy or complex. However, not all tasks are created equal in terms of challenge. Some problems are more intricate than others, demanding a different level of focus and effort. This is where adaptive computation comes into play. It's all about a machine learning system dynamically adjusting its effort based on the task's complexity. There are two compelling reasons why adaptive computation is so appealing. First, it provides a unique way to approach challenging tasks, allowing the system to allocate more computational steps to tackle intricate problems that require a deeper understanding. Second, it offers practitioners the flexibility to balance the cost of inference by dynamically adapting the amount of computation needed for each input. However, existing adaptive models come with their own limitations and shortcomings that hinder them from realizing their full potential. For instance, some models use conditional computation to selectively activate certain parameters based on the input, but this approach can be inefficient and challenging to implement. Other models adjust the number of layers or iterations based on input complexity, yet this can lead to instability and increased complexity during training and inference. Enter AdaTape, a groundbreaking model that takes adaptive computation to a new level. AdaTape is built upon a transformer-based architecture and employs a dynamic set of tokens to create elastic input sequences, introducing a fresh perspective on adaptivity. It's like a modern twist on a tape reader, dynamically adjusting its calculations based on the complexity of the input. AdaTape operates with two types of tokens: input tokens that represent fundamental data like words or pixels, and taped tokens selected from a predefined set known as the tape bank. The tape bank contains all possible tape tokens that the model can utilize. By combining input tokens and tape tokens, the system forms a unique representation of each input, with the number of tape tokens varying according to the task's complexity. This model employs a standard transformer architecture with innovative adjustments to process data effectively. It includes specialized layers to capture the relationships between tokens, distinguishing between input tokens and tape tokens to maintain their distinct representations. One of AdaTape's distinctive features is its ability to create the tape bank in two ways: an input-driven bank that extracts tokens from the input using a unique approach, and a learnable bank that employs trainable vectors as tape tokens. Performance-wise, AdaTape shines across various benchmarks. Particularly in image classification, AdaTape excels, achieving high accuracy with fewer computational resources. On the ImageNet 1K dataset, a widely used collection of images for classification, AdaTape achieves an impressive 83.8% top-1 accuracy with only 86 million parameters and 4.5 billion floating-point operations, flops. This efficiency surpasses other models like VIT and DIT. AdaTape also demonstrates its prowess in algorithmic tasks, such as complex arithmetic problems, consistently outperforming other models in addition, multiplication, sorting, and parity tasks. Notably, AdaTape maintains nearly perfect accuracy while utilizing fewer computational resources. One of AdaTape's significant advantages is its ability to balance quality and cost, allowing users to achieve higher accuracy with a higher computational cost or vice versa, depending on their specific requirements. Unlike some adaptive models that change the number of layers based on a halting system, AdaTape employs a fixed number of layers, ensuring stability and preventing issues related to memory and speed. In summary, AdaTape introduces a novel approach to adaptive computation that redefines how machine learning systems handle tasks of varying complexity. By combining dynamic tokenization, specialized architectures, and thoughtful design choices, AdaTape achieves remarkable efficiency and flexibility, setting a new standard for adaptive models. That wraps up our exploration of AdaTape's innovative concepts and exceptional performance. If you found this video insightful, consider sharing it, subscribing to our channel, and leaving your thoughts in the comments section. Thank you for watching, and stay tuned for more enlightening content in our next